today's Professor Dr. Orgho Kushum Das, who took out his who took out his valuable time and joined us today to be a part of this workshop. We are honored to have you with us, sir. Welcome you, Dr. Das.
Thank you.
I also would like to offer my regards to all the eminent delegates, our principal sir, and the people joining us today. I guarantee that that this workshop will be productive and worthy our your precious time. Now, without any further delay, I would like to request our respected principal sir, Professor Dr. N.C. Ghosh, to share few words, sir. Sir, over to you.
Yeah, thank you very much, Tanmay. It's a pleasure for me to be here with in the inauguration part of this particular workshop. So I heartily welcome our guest, the collaborator, Dr. Orgho Kushum Das, and also our Miss Head of Computer Science and IT, Dr. Shanta Poni, Dr. Orpita Chakraborty, and also all other guests who are there in this particular inauguration, together with the delegates for this 3 days workshop. It's nice that as Professor Tanmay Pal has said, that it is being organized by the Computer Science and Engineering together with IT, along with the IIC Institution Innovation Council of BIT, in collaboration with ON Institute and Open Power Foundation of IBM. It is being organized under the framework of an MOU that BIT has executed with ON Institute in the year 2020. So this particular workshop is on data science. So these data, as you all know, because I am not a computer person, what I could hear from different corners, that data science nowadays, it has got a lot of future prospect, and it is the need of the time, and it has got a lot of opportunities and scope in time to come. So definitely it is going to give us a lot of flavor in coming 3 days workshop. So in this particular workshop, we, in addition to Dr. Orgho Kushum Das, who is now with the University of Alaska, Fairbanks, we will have Dr. Amartya Huta, who is Pidley Investments. He is a data scientist, and also Mr. Ganeshan Narayanasamy, who has also executed the MOU with us, who is a IBM global leader on open power, and also Miss Sri Kamani, tech lead object automation services private limited. So they will be giving you the particular expert lectures in this 3-day workshop. In addition to we may have some more experts from BIT as well. So I heartily welcome all of you to this particular 3 days workshop. So with regard to the BIT, for the benefit of all our experts, as well as the participants other than the BIT faculties, BIT, it's Bengal Institute of Technology. It is located near to Bantola on the Bashanti Highway. It is about, say, you can say 8 kilometers away from Science City. So we run 4 streams, undergraduate streams. It is computer science and engineering, information technology, electronics and communication engineering, and also biotechnology. So we have, as of now, you can say students, total strength of the college with regard to the students is below 1,000. It is 850. And we have faculties about 44. in all course streams. So having the size, you can say it is not a big size, it's a small size, but our students and faculties, all our students and faculties, they have got very good relationship among themselves in the form of, say, faculty in the form of mentors, and students, they aspire on different projects, like they generally participate in Smart India Hackathon and also Banglathon and all other contesting events, and they also claim awards. So these data science and also anything with regard to the, say, computer application, coding application, my students will be benefited through our faculties, no doubt about it. The faculties, they are updating their knowledge and also they are translating the knowledge. The beneficiaries are the students. And by and large, as end product, it is the college that gets the flavor and benefits of all these activities. So this is particularly with regard to the Bengal Institute of Technology. In addition to that, this institute has got this institute does some R&D as well, and our faculties, they publish their, although they deal with the undergraduate, but they do research, and they have number of papers published in journals, good journals. So I feel myself really elevated when I talk about all these things. So with regard to the MOU we have with the on institute and also open power, this has got specific objective. This MOU will help enable collaborate development on computational technologies, including an open ecosystem to serve the evolving needs of society, customers, and industries. This is the precise objective, and there are other details also. So under this MOU, this is the first workshop we are conducting, and we hope that this workshop will be successful, and if we are very much successful, and if we find very good results, definitely in time to come, we'll organize some more workshop. So without going further details, because there are other speaker as well, so I will say welcome to this workshop and enjoy the workshop. And I also heartily welcome all our speakers to this online workshop. And I think we'll take the benefit of all the experts we have in coming, we'll have in coming 3 days. Thank you very much. Thank you. About to Professor Tanmoy Pal.
Thank you very much, sir. Thanks for your inspiring words and valuable insights of our institute. Now, I would like to request our respected HOD, Madam of Computer Science, Engineering and Information Technology, Professor Dr. Shanta Phoni, Madam. Please share a few words. Over to you, Madam.
Thank you, Tanmoy. Good morning, Dr. N.C. Ghosh, Principal, BIT. Dr. Orgo Kushum Dash from Institute and Open Power Foundation. Dr. Urpita Chakraborty, President, BIT IIC. All the respected faculty members of BIT and the participants. Warm welcome to you all from on behalf of the Computer Science and Engineering and Information Technology departments of BIT for this 3 days workshop on data science and art for future. So as you all know, the focus of this workshop is upon a very contemporary and a relevant buzzword called the data science. And we are very much sure that from this workshop, our participants will learn, enjoy, and enrich themselves. So we have had the privilege of successful collaborations with Dr. Das before also on many occasions. And we look forward to have much more such collaborations with his team in future. And from the side from the Department of CSE and IT, I want to say that we will be having more such collaborations, as well as the workshops and FDPs being conducted by the department in future too. So my best wishes to the resource persons, the organizing team, and IICBIT for all their help and support, and all the participants for being here. Thank you so much.
Thank you, madam. Thank you for your inspiring words again and valuable insights about our department. Now, I would like to request Professor Mautan Mukhopadhyay madam to continue the session from this point. Over to you, Mautan madam.
Thank you, Professor Tanmay Pal. Good morning, everyone. Myself, Mautan Mukhopadhyay, Assistant Professor of Computer Science Department. I would like to welcome our guest speaker, Professor Dr. Orgho Kushum Dash, and all the dignitaries and all the participants on behalf of Bengal Institute of Technology. So now I would like to request Professor Shreyoshi Mitra and Orpita Chakraborty to felicitate our guest speaker, Dr. Orgho Kushum Dash.
Thank you. Thanks a lot.
Now I would like to request Professor Shreyoshi Mitra to felicitate our principal, sir, Dr. N.C. Ghosh.
Yeah, thank you. Thank you very much.
Now I would like to request our head of the Department of Computer Science and IT Department, Dr. Shanta Fani.
Thank you so much.
Now IIC President, Dr. Orpita Chakraborty.
So much. Being the president of IIC, it's really an honor for me. And in the light of Ministry of Education, throughout the year, we try to foster the culture of innovation among the students. And with the collaboration with Dr. Orgho Kushum Dash, hopefully we'll be conducting this type of workshops again in near future. Thank you so much.
Thank you, Orpita and Shreyoshi Madam. Dr. Orgho Kushum Dash is an assistant professor of computer science at the University of Alaska, Fairbanks. He has completed his PhD in computer science from Louisiana State University, USA. Dr. Dash's research focuses on the scalable and efficient analysis of scientific big data. His research also focuses on the secure transfer of big data over the internet using blockchain and other decentralized technologies. Dr. Dash is currently working towards developing an innovative online platform and curriculums to spread quality education in the field of big data analysis, AI, HPC, and related technologies. In this session, Dr. Dash will discuss about ON Institute and the Data Initiative, Data Education Initiative, and also cost-effective acceleration of genomic analysis utilizing modern big data analysis techniques and modern distributed server infrastructure. In today's session, Dr. Dash will discuss the recent advances in large-scale experimental facilities ushered in an era of data-driven science. This large-scale data increase the opportunity to answer many fundamental questions in basic science. However, this data pose new challenges to the scientific community in terms of their optimal processing. So without wasting much more time, I would like to request our guest speaker, Dr. Dash, to start today's session. So before starting the session, I would like to request all the participants to be on mute throughout the session. If they have any questions, they can ask after this session.
All right. So should I start?
Yes,
Sir. Yes, sir.
So
Okay.
you can start.
All right. Perfect. So first of all, good morning, India. Good morning, Kolkata. And Before going to my presentation, I would like to thank the organizer and the entire BIT family, including the students and all the teachers, for inviting me and for collaborating with Institute. And in this entire 3 days session, we will be going over many different aspects of data science. We will mostly focus on the education part, how the teachers can teach the students, how the students can improve their learning experience, their learning outcomes can be improved and all those things. And also we will focus on a little bit of the research also. So every day we have divided our talks in a way so that you can get a little bit of the education component and little bit about the research component every day. So, and once again, and big thanks to Dr. NC Ghosh for executing the MO and collaborating with us on Institute and Open Power. And as a result of which we are doing this presentation and this workshop for these 3 days workshop this time. And just for your information, today this entire session I will take care of it these next 1.5 hour. In the beginning, just thanks for tolerating me. Thanks in advance. So anyway, and tomorrow we will have our guest speaker, both from Fidelity Investment as well as from Open Power. And they will give you more insight on what is going on the data science perspective and everything. So every day we will try to get some education component as well as some research components so that you can get a big idea of what is going on, where it is going on, and all these different stuff, bits and pieces of data science. And so just before starting my presentation, another thing regarding the data science. Data science is a hot topic now. Slowly, I mean, from computer, it is not only about computer science nowadays. It is slowly moving from computer science to electronics, to electrical engineering, to civil and mechanical engineering, to bioinformatics, to biotechnology, everywhere. And not only the science and science, technology, and engineering and mathematics, that is STEM, but also the non-STEM majors are also dealing with machine learning and these data science for their purpose. Actually, for example, I had a collaboration with one of the professor from the history department who needed data science. Why? Because they are interested to do some kind of some kind of research on the Vietnam War in USA. So they needed to do some kind of analytics on from which part of the country most of the soldiers participated and all these type of things. And not only that, nowadays you have heard about this non-fungible token, NFT, and all these things, where actually art is converging with data, technology, blockchain, and all these different things. So the idea is like without data science nowadays, the world is becoming the large pool of data, and that you have to analyze. So the students are the future of this data revolution. So with that in mind, let us start today's lecture. And let us see, I mean, if together with BIT College Institute and together with Open Power, if we can improve this education and make this data world a better place. So anyway, without wasting too much, and one more correction I would like to make in our schedule. That was kind of a little bit of fault from my side. So I told like it will be like a 25 minutes followed by an 1 hour presentation. Rather than that, I will just divide it possibly maybe in a 40 minutes or 45 minutes each session. That will possibly give and we will have a break in between two of my talks, and that way everyone will get some time to relax and something like that. So anyway, let me start my first presentation. where I will discuss more about Institute. So let me share my screen. So, all right. So, so here in today's first session, I will discuss mostly about Institute, which is basically a collaborative online education platform with innovative data education curriculum. So in order to understand why I have created Institute and what is the purpose of this MO and all these things, that's what we are going to learn in this presentation. So I will just give you some little bit of background on what is the current state of data education, where we are moving, what are the best practices for teaching and learning and all these things. Those are the things I will discuss. So, all right, once again, I am Arghya Kusum Das, an assistant professor of computer science in University of Alaska Fairbanks and an advisory board member of Institute. So, let's start today's session. So, first of all, what is the current state of data education? And if we see all these different things that we will see that large-scale experimental facilities, engineering facilities, enterprise experimental facilities, computation, machines, mobile phones. In our life, we just started getting a lots of data from all the different sources. So in order to handle that data sources, lots of different types of technologies are required. We need different types of programming models, map reduce, graph processing, NoSQL. We need different types of performance analysis tools. We not only need different types of programming models, but also the analysis types are being changed. What should be an optimal for batch analysis tool? What should be an optimal way to do interactive query analysis? What is an optimal streaming analysis idea? And all these different things. Not only these, on the other hand, hardware also are changing. The performance point is also changing. So the disk-based hardware, so hardwares are like disk-based, in-memory, CPU-based, GPU-based. So lots of different things are changing in all these domains. And if you analyze the market, if you analyze all the different tools and technologies that are available to us, for every different types of these programming models, analysis type and hardware types, you will see different tools are coming every day. So for example, like if you consider MapReduce for batch analysis on a disk-based computing, that is nothing other than Hadoop. Then let's say if you are talking about NoSQL for interactive query and then in memory, there is a tool called Hazelcast. Then NoSQL interactive query for disk-based computation, that's H-base. So if you take every combination, you will see that new tools are being proposed every day. So the technology is changing at a very high pace, and as a future worker, all the students need to learn all those different tools. So what is the best way to learn the tools? That's what we need to figure out. Of course, we need some different types of strategy. And well, not only the data, but on the other hand, these deep learning and machine learning, deep learning, statistical learning, lots of different machine learning techniques are also being proposed. So what are the fundamental different things that we need to learn? Those are becoming our learning objective. How can we make our learning better and be much more productive in an industrial setup or in a research setup? And on the other hand, not only the big data and the machine learning high performance computing domain is also changing. Every other day, CPU speed is increasing. Intel is coming with their own hardware. IBM is coming with their own hardware. So how to keep up with all these innovations? How to learn the basic fundamental things so that you can be productive in the industry? That's becoming the major question. So basically the question is like, and also during the COVID, what we have seen that there are different types of mode of education have come into the picture. For example, like there are offline mode where they are always, and for example, like with offline mode, the major challenge is like, well, it normally responds slow with the technology changes. Like it totally depends on the personal interest of the instructor, limited collaboration opportunities. You have to be geographically confined into your area. So all these different problems were there. Now, after the COVID, we have seen that there is a big initiative for the online education, and possibly I am doing the webinar today. Possibly that was one of the motivation. During the COVID time, we have signed the MOU, and we have realized that what is the benefit. I mean, what are the benefits and of online education, and that's why we are doing all these webinars and workshops and everything. So anyway, but well, in online education also there are several type of pros and cons. Some of the cons are like, let's say there are lecture heavy materials, skepticity about the ability to apply for the skill learned, whether you are being evaluated properly, are you learning properly by yourself. So all these things are big challenges. And also there is a hybrid mode of education that came into picture. So where actually partly we are doing the data education or anything, partly online and partly offline. So possibly most of the times we are mostly familiar with this hybrid education in this era. And but the question is it enough for big data education? What are the limitations and how to overcome that? So here is the issues and challenges. So the challenges are mostly like the course structure related challenges are there. For example, like mostly it is like online education means it's an asynchronous arrangement for lecture and hands-on. You get the video lectures first, and then at some point of time you are doing the hands-on materials and everything. So there is not much relation between this lecture and hands-on experience. And sometimes it happens like, well, after the lecture, since you are not doing the hands-on at the same time, the students start forgetting what is happening. So so these are some of the problems related to the course structure, as well as there is a big problem for course infrastructure also. For example, like there are many colleges, many universities across the world who really does not have any high performance computing resource, who really does not have too much, many GPU, like 4 GPU based computer, 8 GPU in one computer, lots of high performance server or a data center. Many universities and colleges cannot afford that, and it is not even possible. So there is a strong gap in that aspect also. So what is happening? The students are learning the theories in the university, and when they are going to the industry, they are a little bit lost. So lost means there they need to work on this high performance server with hands-on. But since the university did not have the infrastructure, which is quite common in all the places over the world, their learning are not totally completed, and they are definitely suffering in the industry, and they need to get the develop the skills from the scratch once again. So these are all the different types of problems. So as a result, what we are seeing that, well, in the first beginning, when you start learning the theory, the students start learning the theory, then we are getting a lots of the learning is good, but in the end, when it really comes to applying the knowledge, then we are seeing lots of different issues. And it's not only in one specific country or one specific country like India or any type of developing country. It's the case everywhere, including USA, including Europe, in different countries in Europe, every places. And also, when we consider like these online education things, we have seen there is an enrollment related problem also. Students start with a lot of different interests, but eventually they lost the interest because of the lecture heavy materials, because of the video quality and all these things. Now at Institute, actually, we are trying to address all these issues, these course structure and infrastructure related issues. so that the students' learning need is satisfied, and also they can be productive in nature. So basically what we need is we need a very collaborative solution, just like this workshop or webinar today. We need a full collaborative solution, and collaborative solution does not mean only collaborating with one industry partner or only, let's say, another university or something. That is not the meaning of full-fledged collaboration. Here, by saying collaborative solution at institute, we mean a unified learning solution or a unified learning ecosystem for an improved collaborative education. So here, basically, collaboration happens, sir. Collaboration happens between the learning solution, software, containers, and optimize for the hardware. So all these different aspects we really need to keep into mind. We need to collaborate with multiple different parties where we will get all these four components into education. If we need to blend all these four components by means of collaboration into our education to make data science, data education better. So here is so what we are doing at institute, we have divided the learning solutions into different levels. Let's say 100 levels for beginners. So here we are doing a lot of research regarding this data education because it is new, and in many places it's being done in a very haphazard way. We have there are lots of noise in the education. Noise means, I'm saying, like, well, you may need to learn it way later in your educational stage, but you are being taught it in the very beginning. So that way your learning needs are not quite satisfied. So what we are doing here, we are identifying the fundamental components here to make the learning better. So here we divided the data educations for many different things with 100, 200, 300 levels. For example, in the 100 levels, you will learn only the inception and histories, several components, a little bit of application, and let's say a little bit of coding on the pre-configured infrastructure. Then you will move to the intermediate level, where you will learn a little bit of the theoretical basis, then architectural details, how architectural details are impacting your solution, how you can improve it by changing several configuration, how to deploy your code on the server, how to deploy it better. So all these different things you will learn in the 200 level. Then there are advanced level, where you will learn about, after doing all the configuration and everything, how to optimize my own code, how to optimize different types of computation, how to check all these things, because all these things are required when you will hit the job market. So, and also we have developed several professional course for like these project-based learning, and also different types of consultancy for the professionals from the industries. So anyway, I'm not going into the detail of these professional things, but what we are doing is, we are, just to summarize, we are basically dividing all these fundamental concepts in data science in many different domain of data science into these 3 or 4 different categories, and then we are teaching the students based on their knowledge, based on their capability, based on their interest, what they want to do. For example, I got some liberal arts students who really want to just know the what a machine learning tool can do. I really do not want to teach them these 200 level course. I just want to teach them how to code a little bit with scikit-learn or something like that, a little bit of application related things. So that's their requirement, that's their interest. Based on that, we have to customize the education, data education, for the personal needs, because again, data education is not only for STEM students anymore. It's STEM, non-STEM, liberal arts, engineering, everyone. So this is very important. So anyway, after this learning solution, then it comes like software and middleware. It is very important. So for example, I got one student from petroleum engineering, and he was not even aware of what are all the tools available to do the analysis. So that's what is very important. And in Institute, we have a quite a good framework to teach them about different types of tools and how those tools are fundamentally different from each other. As I have told, there are many different combinations, like let's say disk-based MapReduce means Hadoop, in-memory MapReduce means Spark. Let's say disk-based NoSQL database means it is HBase or some other in-memory NoSQL database, Hazelcast, Redis. Lots of different tools are there, and they are fundamentally different from each other. So how to learn those things? How will you understand that this tool is good for my application? Those things need some conceptual learning, and that's what we offer in Institute Learning. So basically, we teach different types of programming also, and we teach lots of different, I mean, Hadoop big data stack, including like MapReduce, Hive, Pig, Giraffe, Storm, and lots of different things. Also, we teach about the IBM AI Power Stack, where we teach about the Caffe, TensorFlow, then scikit-learn, all these different tools and how are they fundamentally different. And I will discuss more about it in day after tomorrow, I think, when I will discuss about the machine learning curriculum. Anyway, so and also we are working with blockchain related things. And so anyway, so these are the two components. And after that, nowadays, which is becoming really very important in this era of cloud computing and these HPC computing and everything, that is container or virtualization technologies. For example, like Docker, Anaconda, OpenShift, how are they different? What is required for your computation? How are they changing the entire market? How it is helping the faster development to deploy, like, I mean, to develop better continuous integration, continuous development, like CI/CD pipelines. So how are each tools different from each other? Which one is better for your knowledge? So all these different things we need to learn. And well, in Institute, actually, we prepared our learning repository in such a way so that you can easily understand all those differences. So basically here we separated the computation from of different types of computation with computer with the data, which is the hardware. So in this way, actually, we are basically segregating different types of different parts of the data education. And this is how we are teaching our students to make them job ready, make them production ready. If the students is interested in the software, we are confining themselves them in based on their interest. Of course, we are giving them the knowledge for this computation part with these containers, pre-packaged and all these things. If they are interested in more deeper, we are teaching them how to prepare the container. If they are interested in the data storage, then we are going for this type of part. So this way we are basically dividing this data education into different way, and then we are collaborating with all these different hardware tools, as well as manpower, I mean the teaching resources and everything, to do better data education across the world. So finally, of course, there is hardware related things also. Every day the hardware actually changing the performance point. The SSD, NVMe SSD, SATA SSD. On the other hand, processing, like well, every other day NVIDIA is coming up with their new lines of GPU, sometimes GTX, sometimes Pascal, Volta. Which one is better for your computation? And whenever new hardwares are being proposed, AWS or other cloud-based service, they are also started offering different types of cloud infrastructure for many different purpose. Now, if you want to use one cloud infrastructure for your course or somewhere in your industrial project, how will you know that this cloud infrastructure is better for my purpose? To make those informed choice, you need to learn all these things in a pretty fundamental way and in a different fashion. So those things actually we are trying to clarify in Institute by collaborating among all these four different components of education. So you will learn on top of the software and middleware and the containers, which are and the optimized hardware. And when you will have this entire things ready based on your interest, then you will have a better knowledge about the world, which one is good for your purpose. So here are some of the use cases basically, and this is just for the showcasing use cases, like the students, we have several academic projects where actually we collaborate with many different universities and on different types of projects. And there are several industry students also who learn new different topics for their next project. So we actually mentor them in a synchronous fashion over Zoom or over any other mode of communication. So they get personalized mentoring for all these things, either in academia or in industry. So some of the example projects are like these genomic analysis, which we are doing with some US-based universities. And then there are some healthcare data interoperability, which we were doing with Amity University in Kolkata. There the students were doing lots of different things with blockchain. And also we have some pretty cool and fun projects also, like movie analysis, like how can we classify the genre of the movies, like, how can, not just by seeing the movie reviews or the summaries, but analyze the entire trailer video to come up with the genre. Take the video, break it down frame by frame, do the image analysis, do the subtitle analysis, subtitle analysis, as well as the soundtrack analysis, do all these different things to come up with genre, so that and then you can understand, right? How we are mixing all these different things. So text-based analysis for subtitle, image analysis for video frames, and soundtrack analysis will give you the time series data. And this way you will, with a fun project, we are basically teaching our students about many different types of things in machine learning. So these are the different types of activities we are doing in academia and industry. And so here basically is the Institute website, which is up and running. And these screenshots are pretty old. It is showing only 15 registration, but actually there are more than 1,000 registration already. And we are working with many different universities across the globe, including TU Delft and everyone. So after this presentation, maybe I will play a small video that I have prepared, and then you can understand what is going on. So here are some of the some of these activities and some of our screenshots. In Institute, actually, you can download all these images. I was talking about the container image. So if you are having a lot of trouble in setting up the infrastructure, let's say you want to make a pipeline with TensorFlow and Hadoop, but there are some problems coming with versions. So don't worry, just download our containers or our virtual machines. We have everything set up. Just set it up in your machine and start working. Be productive and right now, right away, and then focus on the configuration later. So that, the thing that I am trying to say at Institute, you are not actually bounded by or there is no showstopper for your learning. You are not being able to do the installation, that's okay. Just go with our virtual machines or the containers and start learning the coding part. And then let's come back, and then we will do the installation and all these different things. So there is no showstopper the way we teach them. And also this is basically the institute one one sample web page, course web page, where you can basically see that, well, there are panels for video lectures, and at the same time you have the panel for doing the hands-on practices also. So here, once you will you can play and pause the video, and you can type your code in this panel, and you can get the results. So this way we are tackling the lecture heavy and the hands-on, I mean the asynchronicity between asynchronousness between this lecture heavy material and the hands-on in this way, by providing both video lectures as well as hands-on opportunity on the same page. And well, the other thing is these pages, based on the subscription, these pages may run on a real web real high performance computing infrastructure. For example, this screenshot was actually based on an on a supercomputer which is running at University of Oregon. So here, this Jupyter notebook is basically a gateway to access a supercomputing cluster, so that you can learn how to develop and data application at scale, how it is behaving on a large scale computer. The behavior is pretty different in a desktop and those type of supercomputer, where it has, like, let's say 256 gigabytes of RAM, 40 different CPUs, 4 different GPUs. The behavior, performance standpoints, and everything is pretty different. So just in one page, you can learn all these different things. And also, as you can see, we have the synchronous training opportunities also over Zoom, or everything you will get on the same page. So the boundary of the learning, online education, has just got extended. In Institute, we have we have just overcome that by developing this type of new teaching tools. So yeah, so and here, as you can see, like many different types of infrastructure you can access, starting from Amazon EC2 to different supercomputer, Power 9 based supercomputer, Intel based supercomputer, and everything you can access, or you can integrate to your own system also. So all these different things are there, and I will invite all of you to look at the web page, and we can help you based on, and since this is just a start of the collaboration, I will be very happy to help you with all these tools, whatever we have, in more detail in some time. But anyway, so just for the sake of time, I really do not want to go into the detail of all these demo. Maybe that will be the part of some future workshop. But anyway, so here is our future goals. We want to improve the learning infrastructure for data collaboratively. So data, AI, HPC based education, irrespective of the geographical boundary, we want to make it better. And we want to spread the data education and across the globe, better data education across the globe. And at Institute, our goal is to make the data education accessible, affordable, and available to anyone, anywhere, at any time. So anyway, if you want to participate at Institute, any of the Institute project or anywhere, you can contact me. And if you are looking for if you have any type of data or learning related question, or want to see some kind of course, some innovative course that you think is better for your student, or if you think better for yourself or anything, and some kind of if you want to get involved in some kind of cool projects, collaborative research projects, you can contact us. And well, recently we have started some grant opportunities where we are really interested to set up infrastructure at the university campus, and we started accepting the proposals. These are mostly like the infrastructure related grants, and where we can see, like, well, these things has really very good potential to improve the education and everything. We are funding them or helping them with our resources. So many different, this can generate revenues for the universities as well as for institute, as well as it can help the entire community. So all these things are there. And if you are interested in designing some new courses, or anyhow, if you want to contribute, like educate the people with your own software or hardware, all these things, for anything, any ideas, please contact us. We are very much open for collaboration. So that's about Institute. And well, all these, we have a big collaboration with many different universities and industry partners. Here are a few, of course. There are a lot actually, which are not in this list, but these are like who supported us from our beginning and like that. And so that's about, so, and it is now it is not only for the beta user, but it is open for all. And well, so that's all my first presentation and about Institute. Now I'm open for question.
If any participants has any questions, they can raise their hand or directly write into the chat box.
Siddhartha Shankar Ghosh, I think, raised the hand.
Yes. Siddhartha, unmute yourself.
Hello. Hello, sir.
Hello.
হ্যাঁ স্যার বলছিলাম কন্ট্যাক্ট করবো কিভাবে আপনার সাথে?
I have my email ID here, akdas@alaska.edu. And you can also find me in my LinkedIn that I will share in my next PowerPoint.
Okay, sir.
Make sense?
Okay.
Sure. How GPU is used in data science? Well, GPU is changing the data science, honestly, Siddhanto. So what is happening, like, well, all these machine learning related things, not all, but many of the machine learning related things you can think of, they are basically nothing other than matrix multiplication. All right, not only matrix multiplication, but let's say linear algebra and different types of matrix manipulation. Now, these matrix manipulation can be made tremendously faster if you use GPU are optimized for that type of computation, you know. So that's how, I mean, so now you can understand, since machine learning is mostly about this matrix manipulation related things, GPU can tremendously make those applications faster, especially when it comes to learn from a data. Let's say you have a 1 billion data points and you want to learn from them. So that means you have to do a lots of matrix related operations. And sometimes if you do not do it in parallel, it may take like days after days and weeks after weeks also. And if you use GPU, you can get sometimes like 100 to 200 to even like 500 times faster performance compared to a CPU. So basically it is coming from that matrix multiplication, which can be parallelized using GPU, and thus GPU is helping. And of course this image is significantly faster image analysis, because image is nothing but a matrix basically. So whenever you will find a matrix, that can be made faster with GPU, and that's how GPU is helping text analysis as well as image analysis. Yeah, Dr. Ghosh.
Thank you very much, Dr. Das. It was very nice lecture. It has a lot of contents. I have a small query. You know, the query is, you said that okay, you have some provision of grant for infrastructure development. So can institute like BIT apply for
Yes,
that grant? And what type, how
yes,
much
yes.
amount, do you generally support?
So, well, for the amount and all these things, let's take this discussion offline after this workshop,
Okay.
maybe.
Okay.
And we support. I mean, well, because that depends totally on based on US market and India market. All these things are different, right? So that depends on the market. And well, of course, I encourage BIT like institute to apply for these type of grants, and so that we can develop our infrastructure in many different places. And because that's our motivation, because our motivation is to improve the knowledge base across the world. As I told, like we want to make the data education available, accessible, and affordable at anywhere, anytime, to anyone. So that's our motivation. So we strongly encourage BIT like institutions who are serving the developing countries, like India, like some countries in Africa, where there are lots of potential students, but they are not getting infrastructure. So of course, yes.
Second question is, say our students, if they want to do any projects in collaboration with your own institute or you personally, so can they do
Sure.
it? Can they do it?
Yes, sure,
Any
sure.
small project?
So yes, let me share this. Let's say, let me see, so I can show you. Uh, so the students, first of all, they can send me a direct email, and otherwise, also you can do another thing. So let me just show you. Yeah, actually. So let me see whether, yeah. So if you just click on this research, you can see many different types of research students are doing. So AI-based question answer agent, big data management, and all these things. So if you just click on these things, you can basically fill out the form, and then you can be the part of this research. So for all these three different types of researches, you can do the form wise, and well, you can send me per direct email also.
Yeah.
Did I answer the question?
Yeah, thank you very much. Thank you very much.
Thank you, Dr. Dash, for answering all the questions. So, sir, will you take a break, a short break, or will continue?
Yeah, sure. I think it will be better to have, let's say, a 5 minutes break, and then we can continue. How many minutes do we have after this?
Up to 11 a.m. The slot is 9 to 11.
Okay, so what is the time now actually in India?
10:05. 10:05. So we have 55 minutes.
5.
Yes, we have.
All right, so let's take 5 minutes break, and then I am joining.
Okay, thank you.
All right.
So participants, please wait for 5 minutes. Sir will be joining after 5 minutes. So, sir, can we start now?
Yeah, sure.
Okay.
All right. So should I start?
Yes, sir.
All right. Perfect. So, all right. So, well, I hope you had a nice break anyway. Again, me. And once again, thanks for listening to my last talk. And well, thanks in advance once again for listening to me for the next 50 minutes or 45 minutes, 50 minutes. All right. So, okay. So, well, before going to the next talk, let me give you the what I'm going to discuss. So far what we have discussed was mostly like related to the education and how we can do better education for data and all these things. Now I am going to discuss about all these a little bit about my research, what we are doing in here with data. What type of research we are doing, and in that way mostly I will discuss about some of my research, and I will try to give you the idea like where we are moving, because my research is mostly focused on both like developing scalable scalable software, as well as developing state-of-the-art cluster. So we work with many different companies, including IBM, Samsung, and there are several local companies in many different places actually. For example, we have a big collaboration with um, this object automation in India, and we also have some collaboration with Samsung South Korea, and we have many different collaboration, and we have some collaboration with TU Delft University. So with all of them we are doing many different research, but from that I will give you the idea like which will help you understanding where both, like let's say, software is moving from the data analytics perspective, as well as where we are moving from the in the hardware landscape also. So both the things I will discuss. So anyway, let me share my screen once again. And oops. Okay, so here. All right. So can you all see my screen, this PowerPoint presentation?
Yes, sir.
Yes,
Yes,
yes.
sir.
All right. Perfect. Okay, so well, once again, the small introduction. My name is Arghya Kusum Das, and everyone here actually call me Argo. All right, so and I did my PhD in computer science from Louisiana State University. Currently, I'm working as an assistant professor of computer science at University of Alaska Fairbanks. And if you want to reach me out, you can always use this email ID, ekedas@alaska.edu. But the best way to reach me out is finding me on LinkedIn. So here is my LinkedIn profile, but you can just search with my name and you can get me in there also. That's possibly the best way. Anyway, so here is where I am working now. It is University of Alaska Fairbanks. It is Alaska's flagship university. So here, I mean, University of Alaska Fairbanks, that is UAF's research specialties are very much renowned worldwide, most notably for architect science and engineering, and geophysics, space science and supercomputing, and some ethnobotany and Alaska native related studies also. And well, this is possibly the only, not possibly, but this is the only university in the world who has a rocket and satellite launch pad in the university, which is affiliated by NASA Wallops Center, where we work. And well, a little bit about Alaska. I mean, I believe all of you are fascinated, know about this Northern Lights glacier and everything. So here are they. I mean, we are always surrounded by these Northern Lights, all the glaciers and everything. Anyway, and well, the other thing is here it is 6 months day and 6 months night. What you have learned in your childhood, that I see every day in practice. So these are all the different things about Alaska and the University of Alaska Fairbanks, just for the distraction of the topic anyway. So now let's go into my research. And here is my little research overview. My research, as you all know, you already got the idea. My research actually hovers around data. It includes analysis of scientific big data, means developing different types of algorithms, different scalable algorithms, scalable frameworks, different analysis technology to analyze different types of data, including like mostly I work in the genomics and healthcare data area. But anyway, and also it's not only the analytics software framework development, as I told earlier also, I work in the distributed cyber infrastructure development also, where I collaborate with many different industries. I mean, the hardware vendors like IBM, like Samsung, to benchmark their cutting edge hardware infrastructure and propose improvement, propose solution, propose improvement, or propose the optimal cluster architecture for many different companies like that. And recently I have started working on transferring of big data, like using how to use blockchain, like the decentralized technology to transfer the big data. I will discuss about it possibly tomorrow or day after tomorrow, when we will discuss about the research opportunities where everyone can get involved in more detail. Today I have discussed a little bit when Dr. Ghosh asked, but we will discuss it in more detail, what type of projects are going on and what you can do. And also, of course, I mean, one of my close to my heart is andragogy for data education, by which, I mean, because of this, we signed this MOU to make data education affordable and accessible anywhere. So that's that. Because of that research passion, I came up with this institute, and I'm doing all these different things. So anyway, in this in this research, basically in this presentation, I will basically focus on my scientific big data analysis and the distributed cyber infrastructure, the first two things. And that's why the name of this presentation is cost-effective acceleration of big data analysis, utilizing modern big data analytics technique, that is the software, and the modern distributed cyber infrastructure, like all these HPC and supercomputers and all these things. So here is the agenda. I will mostly focus on these first two part in this presentation, that is analyzing the scientific big data and distributed infrastructure for big data analytics. The ongoing research overview, where everyone can be the part, that will possibly come in my later presentation tomorrow or day after tomorrow. And so here it is the introduction. So let's first understand what is the big data. So for the sake of understanding, I mean, I will focus on some two specific application on genome analysis, which have been published in very good journals and conferences. So those research I will discuss about. So for the sake of understanding, I will try to keep it at a very high level so that everyone can understand it. I won't go into the very much detail of these genomic analysis or too much detail of the theory, but I will try to keep it at a high level so that everyone can enjoy it and everyone can understand it. So, first, what is NGS? What is big data analysis? So what are the big data challenges in genomic analysis? So what happened in the next, regarding this genomic analysis, the genome sequencing machines like this one, they cannot read the entire genome in one go. The genome is pretty big. So what this sequencing machine does, they take one plant tissue or the blood cell or something, and then they just read the genome sequence in a shorter fragment. And they actually reads in shorter fragments from the randomly different areas. So what happens after the end product, they actually read the similar regions many different times. So it's just like, let's say you have a multiple different copies of a book, but you have torn apart into many different ways. Let's say you have 10 different copies of the book, and all the pages are just torn apart and here and there from random different places. So it is like that. So, and what happened in the last year, actually, I mean, not last year, so in the last decade, basically, these sequencing machines, which reads the data, reads the genomic data into random fragments, they outpaced Moore's law. Now, what happened as a consequently, they started producing a huge amount of data. And here by saying data, huge amount, we are saying generating the data at terabytes scale. And these terabyte scale data basically producing a tremendous amount of pressure on the high performance computing when it comes to their optimal analysis. So, so that's the big data challenge in genomic analysis. Now, in order to address those challenge in the last decade, in the last few years, many different programming models have been proposed. So here, there are two different models that we am going to discuss today. The first one is MapReduce, where big data is basically divided into small disjoint subsets and then process each of the batch separately from each other without any communication and produce some kind of intermediate result. And then those intermediate results are again aggregated together to give the final output. So that's the concept of MapReduce, and all these outputs are written in a distributed fashion in many different nodes. So for example, like this Hadoop, Spark, they all have this similar type of MapReduce type of programming model based on which they work. Also, on the other hand, there is something called NoSQL, where basically the big data is stored as in the form of a key value format, which is basically a form of a hash table, which enable easy search by key and get the values. Now, based on their storage, whether in memory or disk-based, many different types of NoSQL database are there. Some of the examples you can see in the slide. So not only these programming models, in the last several years, hardware is also pretty much revolutionized. The performance standpoint changed a lot. So if we take a look, if we retrospect in time, we will see that mostly like the cost of the hardware have been decreased and the bandwidth have been increased a lot. And that actually changed the the performance point. So the question was, well, how can we leverage these big data programming models and these recent advances in the hardware infrastructure to accelerate the big data genomic analysis, the challenges that I have discussed a few minutes back, in a cost-effective fashion? That's the question. So here, in order to discuss that, I will discuss two most data intensive application in genome analysis pipeline, and they are pretty fundamental. On top of on top of which basically these many other downstream genomic analysis application depends. So here I'm going to discuss about this error correction application, and specifically I will talk about one type of sequencing machine which is called PacBio and long reads error correction. So let's have some background about these genomic errors and genome sequencing machine technologies. So there are two different types of genome sequencing machines available nowadays. So first one is kind of a Illumina, which looks like this. They basically read the genome in very short fragment, where actually every time it reads at most 100 to 250 characters, and these characters are all like the genomic characters, everything like nucleotide A, T, G, C, something like that. They can read at most 100 to 250 characters. Whereas there is a technology called PacBio, which is basically the name of a company. They can read in a much longer fragment, like 5,000 to 20,000 bases per read. And but now these long reads actually are very much essential for better genome finishing, for more complete genomic assembly, basically better downstream analysis of genomes. Now, but the problem is these long reads have 10 to 15% error, which if introduced in the downstream analysis, you are going to get worse result. It will impact the result of the downstream analysis, and there will be some error. On the other hand, these short reads, this Illumina technology is not that much error prone, where only 1 to 2% errors are there. So the idea is we proposed a hybrid error correction mechanism, means the leveraging the higher accuracy of those Illumina short reads, like only 1 to 2%, to rectify the PacBio's long read, that is 10 to 15% error rate. So the benefit is, of course, this low cost, because PacBio cost is almost like 10 times greater than Illumina. If you want to do only PacBio, want to do the analysis on only PacBio, you have to spend 10 times more. So cost is low, but the challenge is need to analyze a higher amount of data, what we are going to discuss now. So here is an indel error correction steps. I'm not going into too much detail, but just to give you the idea, like, well, the genomic error corrections can be mapped as a graph analysis problem. Now, this graph is basically called the De Bruijn graph, where each small reads, those reads are basically divided into even smaller fragments, which is called a k-mer. And each of the k-mers are basically considered as a vertex in the graph, in a graph. And after those vertexes, and based on the prefix suffix overlap, k-1 prefix suffix overlap, we consider that there is an edge or there is not an edge. So for example, if two k-mers have, like, let's say, k-1 number of strings, the last k-1 part in common, then we consider that there is an edge between those two k-mers, those two vertex k-mers. So in that way, we basically created the De Bruijn graph. And after that, we have done a widest path algorithm, which is known, which is a very popular algorithm in mathematics, in graph theory, which is basically the maximum capacity path problem, also known as that, applied in here to reduce the error. So here basically it says, like, shows the theory. I'm not going into the detail of the theory, but what we have done, we have assumed that KMR coverage as a random variable and IID, and based on and on top of it, we have applied some minimum probability distribution theory to come up with the fact that, well, the probability of the minimum coverage KMR is highest in the erroneous read given by the reads sequence from the same region of the genome. As I told, like it reads randomly from different region, like that. And well, once we have proved that, then it was pretty clear that, well, the widest path algorithm can do much better in our algorithm, in our error correction. But anyway, so here is basically the distributed software architecture. So, well, in order to develop the algorithm, we have used Hadoop and Hazelcast based framework and the tool known as Parlec, parallel long read error correction. So basically, where Hadoop is used for the computation and Hazelcast in an in-memory NoSQL, which is used as a storage. So this framework is one of our big contribution in genomic analysis. So here, basically, this step shows like the De Bruijn graph construction. We have developed a MapReduce based algorithm, parallel and distributed algorithm to construct the De Bruijn graph, which is not a very easy job, and many different other single node tools failed to create that De Bruijn graph on a large scale data. I will give you the idea of large scale in later when we will discuss the result. But anyway, so here we have framed a MapReduce based framework to create the graph. And once the graph have been created, then we have directly stored it into Hazelcast's key value pair, where basically each of the KMR or each of the vertexes are basically their values, and their count and the edges, their predecessor and successor nodes, are basically working as their values. So, and on top of that, we have started doing lots of different types of analysis. And here, actually, this slide shows the theory, algorithm for the widest path. But anyway, these algorithms also we have developed a parallel version of this algorithm and distributed version of this algorithm using a Hadoop mapper only job, where each of the Hadoop worker starts from a source KMR vertex of the graph and then starts finding a widest path to a destination vertex. So this way we have framed the problem. And so these things are basically used for the indel error correction, where indel means insertion and deletion, where it means like some nucleotide character like A, T, G, C are wrongly inserted during the sequencing error, because it is an electronic machine, right? So they have instrumentation error. And also there may be some bases like ATGC have been wrongly removed from the read. So all these things can happen, and those types of error we have corrected using this indel, using this type of framework. On the other hand, there is another type of error which is called substitution error, which means some A is replaced with T or some G is replaced with C, means they have substituted. And that type of error correction, for that type of error correction in that genome, we have used some statistical method using Pearson's median based skew coefficient. Then we have used some majority voting algorithm to do all these error correction, error detection and rectification. Now, I'm not going into the detail of all these things, but well, those things we can discuss if someone is interested in offline, we can discuss. But the thing that I want to let you know that this graph analysis problem and the statistical analysis problem, they are very different in nature. And we have done the framework that we have developed with this Hadoop and Hazelcast, that worked well for both these type of problem because of the robustness of the programming model. And that's one of our major contribution in this field. And here are some of the data set that you can see. in here. And as you can see, we have analyzed like starting from a few MB of East data set to we have analyzed gigabytes of hundreds of gigabytes of human genome data set over here like this. And here are some of the accuracy metrics that we have used. Here are some of the other algorithms that we have tested, like widest path algorithm, the Dijkstra's shortest path algorithm, which one works better. So I'm not going into the detail of all these algorithmic things, but what I want to show you that, all right, so for all these different graph traversal algorithm, like widest path, shortest path, and all these different algorithms, which makes sense in this context, our widest path algorithm works much better here. Percentage read align better, greater number means the result is better actually. So, and with the existing tools, so where existing tools are, there is a tool called LORDEC, which also does several error correction related things. Compared to that, our result is pretty better. Very, so we almost like sometimes our result is almost 11 to 12% better result we have produced. And not only that, we have demonstrated the scalability also, like let's say we have tested our scalability on a computing cluster, like where each node has 20 computational core, Intel Ivy Bridge, and each node has 64 gigabytes of RAM and 256 gigabytes of hard disk drive, and all the nodes are connected using 56 gigabytes per second InfiniBand connection. So on this type of computational cluster with a 55 gigabytes of Illumina and 59 gigabytes of PacBio reads, means almost like 114 gigabytes of data, we have shown that, well, our tool Parlek is almost like linearly scalable by computing over multiple different nodes, 16, 32, 64, 128. So not only that, to showcase our scalability, we have used up human genome dataset where we have analyzed almost 312 gigabytes of PacBio data, means those long reads, and 452 gigabytes of Illumina data, which are short reads, means a total of almost 764 gigabytes data is processed in 28.6 hours with appreciable quality improvement. Now, LORDEC, the existing tools, since it was only single node, it does not have the distributed power. It failed because it cannot handle all the data in one single node. So that's one of our contributions. So this is the type of data we handle at our lab. And so, well, that's the first part where I have discussed about the software and the scalable software framework, where actually we have proved, like, well, we got significant performance gain using different types of modern big data analytic programming model. But the question that we ask, like, well, can we get more by utilizing the recent advances in hardware infrastructure and modifying the hardware organization? So in order to answer this question, we started working towards like the hardware infrastructure. For this, we have actually collaborated with Samsung Research in South Korea and started evaluating their hardwares actually. So I'm sorry. So we have started benchmarking their hardware basically. So this, the first part of the research basically is not too much about the research work or analytical work, but it was kind of manual work basically. So I'm coming to that later. But anyway, so this part of research, so major idea was, in order to understand what is how hardware organization can improve the performance, we basically started investigating that what can be an ideal balance between different parts of these hardware infrastructure. What is an ideal balance between CPU versus memory versus disk, so that it is not very much not bottleneck. The big data analytics is not bottlenecked by one part of the hardware. So that's what our research. And also at the same time, we needed to balance the price also, because it is pretty much evident that if you increase the size of the resources, like let's say instead of using 4 GB of RAM, if you use 256 GB of RAM, of course you will get the performance benefit, but is it supported by your organization? That's what is a very big question from a system vendor's perspective. So that's what we wanted to analyze. Like, can we come up with some easy to use formula to support, to help the hardware vendors to build some kind of cluster, or if we can support some university or some research organization before investment, so that they can use our formula to come up with the actual balance, so that many different applications will be benefited by their investment. So all these things were in our mind, and with that we have collaborated with Samsung. So here in this slide you can see some of these different types of distributed cyber infrastructure where I have worked. So the first one is basically a blade server, which is in University of Wisconsin Platteville. It is a very old Cray server. Here actually inside this box there are 7 different computers. They are mostly known as blade server, where each of these machine has like 2 or 3 cores. I forgot the actual things, but it has like 32 GB of memory, or like 8 cores or something like that. So anyway, here there are 7 different machines inside this box. Then this SuperMIC is basically a traditional supercomputer which is situated in LSU, from where I did my PhD, where each of these machines, many different machines were there. But these machines are similar to the configuration that I have just described, like 20 cores per machine, 256 gigabytes of hard disk, and 64 gigabytes of memory per machine. So this type of machines are like traditional supercomputer. That also we have worked. And then we have also worked in something called hyperscale system, where you can see like each of these small sleek slots is basically a self-sufficient computer. Each of these have like 1 terabytes of SSD, like 4 different cores, and 64 gigabytes of memory per slots. So this is a very unique product produced by Samsung Research in South Korea. And then this one is an IBM computer, a Power 9 computer, which is also pretty unique, which is in Oak Ridge National Laboratory, where it is a very good big data analytic supercomputer for many different purposes. So these are the different types of infrastructure where I have worked. And now I am going to discuss about how did we come up with some kind of balance related formula to help the hardware vendors. So anyway, so here basically we have started delving deeper into the issues of the traditional HPC cluster or traditional supercomputer. We delved into the storage issues, where we have seen like, well, there are very small number of attached devices and they have low IO bandwidth. So that's why when the big data is read by the CPU, that is spending a lots of time read and write from the disk instead of the actual computation. Those things we have observed. Also, we have seen there are lots of memory related issues, and there are several network related issues. All these things we have observed in the traditional supercomputer on this SuperMIC traditional supercomputer that I have just shown. And then we have actually collaborated with Samsung Research. I went to Seoul, I mean South Korea, and worked on their data center to build different types of cluster, basically manually. And as I was saying, the first part of this research was not very much analytic, but it was very laborious work. So we basically went to the Samsung data center and we got several machines, like 16 or 32 machines, and we basically manually changed the configuration in that server room, taking out the slots, taking out the SSDs, put some HD hard disk drive, taking out some slots of memory, reinsert the memory to make it memory heavy, So basically we have just changed it manually in all the different machines to come up with different types of computer organized computer architecture, different types of machines. And based on that, we did lots of different observations based on which our theory is developed. So here basically for the data for the benchmark application, we have used the same genomic analysis application that I have just discussed for the benchmark application. And so here are few of our observations. There were a lot of observations, but the main thing that we have discussed after doing all those changes in the machines and after evaluating lots of different configurations, memory heavy, disk heavy, SSD, HDD, all these things, we have seen that, well, the fewer scale-up server, we have basically seen a trade-off between the performance and performance to price between the scale-up and scaled-out server, where we have seen that, well, fewer scaled up server basically is showing lower performance but yielding better performance to price, whereas more scaled out server producing higher performance but not the expected performance to price. So those were our major observation. And not only that, since Samsung's interest was like SSD, if you know, Samsung is a big supplier of HDD, big producer of solid state drive SSDs. So their interest was like how to deploy SSDs better to improve the performance of a computer. So we have seen this also, like well, one SSD performs almost similar to 4 hard disk drive, and after this adding more disk, like more SSDs, we cannot get the performance benefits because the disk controller basically gets saturated at 500 megabytes per second. So all these things help their development process a lot. So basically those were the observation, the first part, those manual work, and these are the observations. So now the second part, our problem definition was how to model all these observations to develop an optimal cluster architecture, and what is the best way to leverage SSD to get a cost-effective and balanced cluster. So in order to develop the model, we started delving deeper into the old literature, including so Amdahl's computer scientist Amdahl has a second law also, where he told like, well, in order to make a balanced cluster, it must have 1 bits of IO per second per instruction per second. And also he told that, well, 1 bytes of memory is required per instructions per second. So we have analyzed them, and we have started finding the limitations in all these theories. Let's say, so we have found that, well, this Amdahl's law is trying to fit one size to all the applications, but for big data application, it is not at all true. Applications vary abruptly from one application to another applications. The characteristics is totally different. So then we have found that computer scientist Jim Gray, who is the father of modern data science, and he also tried to change this Amdahl's law and told that, well, 0.125 bytes per IO per second per instruction per second application is it is the ideal number of balance. And also he observed that, well, the memory computer balance is rising from 1 to 4. So, but the problem was, these are just like observations. There is no theoretical background, and it may change whenever the price will change, and whenever the geopolitical situation will change, it will change. So, and also it does not consider any type of cost component. So our problem definition was how to modify those Amdahl's IO and memory numbers, those terms, and express it as a function of the application's balance and the costs balance. If we can do that, then this formula will be pretty robust, and it will hold true years after years, and it will change itself and readjust itself with the cost changes and the speed changes and all these things. So that's what our motivation. So in order to do that, we basically tried to keep it simple, because our motivation was to help the hardware vendors, not just come up with a fascinating theory. So what we have done is we have basically divided the entire computation time into CPU time, IO time, and memory time, and we ignore all the overlaps between everything. And in general, it does not hamper the models much. It does not, we do not lose the generality of the model by doing this. And then what we have done, we basically multiplied it with the cost component, and then basically did the theory of finding the minimum, doing the derivations and partially differentiate with Amdahl's IO number and memory numbers to get the balance basically. And then after that, what we have seen, we come up with this type of small formula where this optimal balance of this cluster is basically the square root of the ratio of the application balance between IO and CPU and the cost balance between the disk and CPU. And the similar formula we have got for this Amdahl's memory number also. So now this formula can change year after year. That's what our major contribution is. It is not just an observation, but this theory will change as the application balance or the cost balance will change in future. And well, after doing all these things in the current situation, in the current scenario, in the current marketplace, by collecting all these performance data in the Samsung research lab and our traditional HPC cluster, and collecting the cost data from Amazon, Newegg, many different sites, we came up with the numbers like, well, 0.17 is an optimal number for the IO balance, and 2.7 is the optimal number for memory balance. And then this Samsung cluster was basically developed using they named it, their brand name was Series 2. That was the hyperscale system that I have just discussed. Those systems were basically has the similar type of config, similar type of balance. So here it has like one 6-core Xeon and then one NVMe SSD running at 2 gigabytes per second and 64 gigabytes of DDR4 memory, although only 32 gigabytes we have used for our benchmark. So these type of, so once we have, so this cluster configuration is matching with our balance numbers. Then we have seen that, well, on this Series 2 cluster, basically it is showing the similar type of performance like this traditional supercomputer, whereas we are getting more than 2 times benefit when it comes to performance to price. And not only that, the best part is, with the data size, the performance to price is basically increasing on that server. So for only these 90 gigabytes of data, performance to price was only 2.3 times extra than traditional supercomputer. Here for 452 gigabytes of human genome, it is showing more than 8 times of benefit. So here we have basically to prove our theory, we have tested many different types of configurations, starting from this traditional supercomputer to the data center, to this hyperscale system, which are most competitive configuration basically. So we have tested all these things, and and every time we got basically Series 2 is outperforming in terms of performance to price. And so based on our observation, basically what we have done based on our theory and observation, we have basically put some number and quantitatively divide the traditional supercomputer, data center, and microbrick. We have seen that if the number is this balance beta IO number is less than, if it is 0.003 in that range, that means it is just made for the computational intensive calculations, and which means it is traditional high performance computing or traditional supercomputer. If it is in the range of like 0.015, something like that, then it is like data center clusters come into this range. And this microbrick or this hyperscale system has like our 0.17, this type of range, and these are basically required for all like IO, compute, and memory intensive applications. So these are ideal for big data application, which has IO component, memory component, as well as compute component, and it is not bottlenecked by any of these 3 hardware resources. And not only for the genomic application, we have tested with our formula with different other applications, I mean, which are popular in the market, called TerraSort and word count. And every time we have seen that, well, series 2, whose balance number is similar to our theory's balance number, they are outperforming in terms of cost per performance to power. And the other clusters are showing much worse result. So basically, this beta IO and beta mem can be used to make more informed choice, as I was saying. What is the benefit of this type of balance number? Well, the balance number has a lot of benefit, basically. So the one of the benefit is, let's say, if your organization is trying to invest on some infrastructure for some kind of research work, which is pretty common in our university, and they can use this beta IO and beta mem, these balance numbers, to make an ideal configuration of the cluster and purchase the cluster from the vendor, customized cluster, and which will help their data intensive research. And honestly, this theory have been used in LSU, from where I did my PhD, to purchase a $1 million cluster, basically. And also because they are very much easy to use and more reasonable alternative for flops. Flops means floating point operations, which are the speed measurement for traditional supercomputer, which are mostly focused on the computation. So these balance numbers are much better alternative for these flops, because it focuses not only on the computation but also on the other resources also, not only CPU but memory, disk, and everything. So that's what we have done. And so in this, in summary, we have discussed about this genomic error correction, where I have tried to give you the overview of where we are heading in terms of scalable software development. And then I have discussed about designing some balanced cyber infrastructure, where I have tried to give you the idea of where we are heading in terms of hardware infrastructure. So that's all for today's lecture, and these are some of my publications, and that's it for today's lecture. So I'm up for questions.
Thank you very much, sir, for your wonderful session. If any participant has any questions, they may ask in the chat box, or unmute yourself and ask the questions to sir directly.
I think there is something in the chat window. Okay.
Any questions?
Sir, what is the configuration of big data analytics supercomputer?
Big data analytic, well, the configuration can vary a lot. So let me go to the present, let me go to this one. Let me see which slides has its configuration. Yeah, so here is one sample configuration. So it is the series 2 cluster, which shows the best performance and best performance to price. And here it has like one 6-core Xeon running at 2 gigahertz and one NVMe SSD, which has 2 gigabytes per second IO bandwidth and 64 gigabytes of DDR4 memory. So here basically each of these slots, as you can see in here in this picture, has this configuration. And this chassis possibly has either 32 or 21. I forgot the number. Okay, I mean how many? Oh, okay, here each chassis has like 32 different nodes here and here. So this is a sample cluster, but well, it does not, you do not need to stay with this 6-core or 2 gigabytes per second. But the point is, if you increase the CPU, you have to increase this IO bandwidth also. Let's say from 2 gigahertz, if you make it 6 gigahertz, then you have to change it from 2 gigabytes per second to 6 gigabytes per second. So maintain the balanced numbers. That's it. Did I answer correctly?
Sir, another question is there in the chat box. What is it mean by data in genome sequence?
Okay, so data in genome sequence means text type data like this over here. So these things are basically the reads. When you get the data from this Illumina or PacBio, these genome sequencing machines, they are nothing but sequence of A, T, G, and C. Everything is happening within these 4 characters. And these 4 characters conforms like, well, millions and billions of reads, yielding like those terabytes of data, hundreds of gigabytes or terabytes of data. It's all ATGC in different sequence, happening many different times. That's the data in genome sequence.
Is there any chance to losing the data in genome sequence? Another question.
Of course, yes, it has. There is a chance. As I told, like, well, these instruments, this PacBio has indel errors. So indel errors means some bases like these A, T, G, and C will be erroneously inserted, and some of the bases will be just eliminated, removed, means data loss. So that can happen. That is pretty common, and and common means it can happen in 10 to 15% error rate, which is not less. And this entire research that I have described, this error correction, is to eliminate that error, to rectify that error, basically.
Then, sir, it was my question. Then, sir, how to retrieve those data? Those data which are getting lost, then how to retrieve those things? In genome
That's a good
sequence,
question. So, yes, please go ahead.
when the data is getting lost, then how to retrieve those data?
Yeah, that's what this De Bruijn graph is doing, basically. So here, as I told, like all the reads, I mean, one part of the genomic region are read multiple different times. Let's say it's just like the fact, like you are tearing the books, some part is getting like, let's say 1 to 10, and some other part is getting like 1 to 20, some part is getting 15 to 25. So multiple different times the same region have been read again and again and again. So using this graphical analysis by dividing into even smaller regions, we are basically trying to find the relations. So it is exactly similar, like let's say you got 1 to 10, then you just tearing the book pages, 1 page at a time, you make it even smaller, and then just found like, well, page number 1 and page number 2, you are trying to match the last line and the first line of those 2 pages. So that way we have found the lost part. So they were there in some of the reads. Some of the reads are correct, some of the reads are wrong, and then we basically tried to connect all those small parts and then again reform the entire book or the entire genome. Did I make it, or is it still confusing?
Yes, sir.
Okay, sir, thank you.
Yeah.
Any questions from participants? And
I think one question was there. Somebody asked that we need supercomputers for the big data analytics, or we can do it in cloud. That was the first question in the chat box.
Well, that's actually the point of confusion. Now, for that, actually, we need to understand the differences between cloud and supercomputers. All right. So first of all, cloud is a business model. A cloud can also have a supercomputer. All right. So cloud means platform as a service, software as a service. Everything is here. And a supercomputer and a cloud infrastructure can have similar type of configuration. Now, well, most of the time it happens like supercomputers are focusing on better CPU or better GPUs, whereas clouds basically focus on all the different things. They focus on the business applications where you really do not need too many computations. So to answer your question, given that you understood the difference between supercomputer and cloud, supercomputer is the hardware configuration and cloud is the business configuration, let's say. Given that you have understood that, one thing, for enterprise data analysis, we always use cloud infrastructure because you can get it at much lower cost, because cloud is like pay as you go model. And for and enterprise data does not normally, it does not need too many computation like research. And for research application, mostly we go for the supercomputers, where we mostly focus on the computational cycle and all these different things. So totally based on different types of applications, you have to select it. And once again, it does not matter whether it is a cloud or supercomputer. As I was discussing over here, your configuration should be like this. If you have a data intensive application, it must go with this balance number. And this way you can get better performance.
Thank you, sir, for answering all the questions from the participants. So now it's time for feedback. So please, anyone, either Sriyoshi madam or Upita madam, please share the feedback link. Yes, feedback link is shared in the chat box. Please fill this form.
फीडबैक लिंक भर के जा रहे हैं, रुक जा.
Thank you once again, sir, for your wonderful session. So,
sure. And one request. So since you are getting the feedback form, can you share the result with me? Would you mind?
Yeah, sure.
Yes, sir.
We'll share the details with you. Sure.
Thank you. So hope you all have enjoyed the presentation, and tomorrow we will meet again, and tomorrow we will have two external speaker, one from Open Power and another from Fidelity Investment. And from them, I'm pretty sure you will learn much better about data science and which direction we are moving. Thank you. Thanks for listening. And once again, thanks to the BIT team for organizing all these things, and thanks for collaborating with Institute.
Yeah, thank you very much, Dr. Das. It's from NC Ghosh. Right? Yeah, thank you very much.
Dr. Ghosh. Sure.
Now we are concluding today's session. So thank you all the participants for being with us. And tomorrow all participants are requested to join sharp at 9 a.m. So see you tomorrow. Okay.